Okay, we're ready now to take this kind of data, but for all the genes in our data set, and produce something called a volcano plot, which is a popular representation of the impact that any treatment or condition, any pairwise comparison has on all the genes in our data set. So that's the next code chunk. I'm going to open that up. And the first thing I see is just a comment or a reminder to you and to me to go back up and set that top table function to capture basically all the genes in our data set. And this is kind of easy and convenient because we can actually set this number over the number of data points or rows that we have in our data set, and it'll just take everything. So we don't need to worry too much about exactly that number. Just set it higher than the number of rows in your data. So when we do this now, our top table isn't the top genes, it's everything, and it's all the stats for everything too. It's all these same stats, but now it's every gene in my data set. I'm not going to convert this into a tibble. I'm not going to try to view that obviously as a table here. I'm going to skip over those two bits and go back down to my volcano plot. And what I'm going to do now, actually, sorry, I am going to convert that to a tibble because we want to do some plotting of it, and it needs to be a data frame or a tibble here to work with the tidyverse tools. So I did just run this bit, right? But I'm not going to pass that to GT and ask it to make a 40,000 row table or 30,000 row table. All right, so now that I have all the statistics here for all the genes in my data as a data frame, right? 15,944 observations of 7 variables. This is what that looks like: gene ID, log fold change, everything, all the stats we just talked about. Now that I have all that information, making a volcano plot is really easy. Volcano plots just plot the log fold change by the adjusted p-value. And in order to make it appear as a vertical volcano or a V shape, it plots the inverse log 10 of this adjusted p-value. So I have all the data I need in the form I need it for making this volcano plot. I just need to make sure I sort of change that adjusted p-value when I plot it. So I'm going to call on ggplot and give it this data. I'm going to set the aesthetics, and the y-axis I told you is going to be that adjusted p-value, but I want it to be the inverse log 10. And I can do that directly in the aesthetics, right? I can go ahead and sort of transform that data right here in place. I want the x-axis to be the log fold change, and I want to go ahead and set a text mapping aesthetic to really be this phrase symbol. So I'm using the paste function, symbol, colon, and then I want it retrieving the gene ID column. So I want it retrieving the entity here in that row, the value in that row, and appending to the front of it symbol. This will not show up in the initial static ggplot I use, but it will be available when we produce an interactive volcano plot. I want a geometric point, and I'm going to go ahead and set up some labels of a title, subtitle, and caption, and apply this regular theme. All right, we'll go ahead and run that ggplot code and see what we get over here. And this is a lot of data points. It's, whatever, almost 16,000 data points, but it'll display reasonably quickly here. And now we have this nice volcano plot where we see log fold change, and this is disease minus healthy. So things to the right here with positive log fold changes are genes upregulated in disease. Things that stretch to the left are things that are higher and healthy, so they have a negative sign. So these genes here were much higher and healthy. They're much further to the left. These genes here to the right are much higher in disease compared to healthy. All right. So I also told you we transformed this adjusted p-value or FDR to make it the inverse log 10. That means that genes that had very, very low adjusted p-values now appear very high up. And so now we have this very useful visualization that lets you understand magnitude of change on the x-axis and significance on the y for any single pairwise comparison, right? Because this log fold change is just representing a single comparison. So now I know these genes are changed a lot, induced a lot in patients with disease, and are very, very significant. These are more weakly induced, but are still very significant. These are induced a lot, but have higher p-values, right? So maybe borderline significant or less significant, and so on and so on. So I'm sure many of you have seen these volcano plots before, but I just wanted to orient you in case you had not seen them. Now, this is great, and I can go ahead and annotate this, and I've provided some suggested annotations for you, including things like geometric horizontal lines using the geom H line and geom V line functions. You can set where you want a line to strike, vertically or horizontally, what you want that line to look like, long dash, and what color using hex code conventions here. You can choose a color that you'd like. And now when we run this, we will get the same plot, but now we've demarcated cutoffs, right? Because differential gene expression is all about setting arbitrary cutoffs, a p-value of 0.01, log fold change of 2. And so we can set these vertical lines, right, and indicate them with different colors, dashed lines, horizontal and vertical. That matches my H line and my two V lines. And clearly, this V line here at +1 is red. That's the hex code for red. And the V line at -1 right here is blue. Okay. If you don't like that look of these geometric line objects, you can also annotate with rectangles, and you can set them to be sort of semi-transparent by setting the alpha. You also can control the color, red and blue, and that gives you a different look for your volcano plot, which will pop up here in just a minute. And these all give you different ways of basically making publication quality volcano plots that highlight to readers that you have differential gene expression in this pairwise comparison, and the numbers of genes that might fall in there, and you could pull that out and annotate the actual rectangles with the numbers that are here. Okay, so that's great, but we have no idea what this data point is, right? And so, not for the purposes of publication per se, right, because we can't publish interactive graphics, but for our own utility and in sort of our data analysis, it would be great to be able to mouse over any of these points and know immediately what gene we were dealing with. So I'm going to turn off these annotations for now. I'm going to reproduce the basic volcano plot without any of these colors or vertical lines or anything, and I'm going to save it to an object called vplot. And now that I have that ggplot object called vplot, I can now pass that to Plotly using the ggplotly function, and it will make this an interactive volcano plot. It'll look almost identical to this, except now this text mapping aesthetic will now be really valuable to me because it'll actually give me a pop-up of exactly what gene that is. So I just ran that line of code. And of course, this is now interactive, so it takes a little bit more memory to run this. It's not going to pop up in the plots tab. It's going to pop up in the viewer tab because it's an interactive graph. And when this displays, I will have that mouse over capability. Okay, so same plot, but now I mouse over any data point and I get its log fold change, its adjusted p-value, and the gene symbol. So based on my top table, right, we might anticipate that this gene's MMP1, biggest fold change, and sure enough it is. And I can mouse around and see that there's lots of GBPs and interferon response genes, but also a ton of these Ig immunoglobulin genes that we already saw in our top table. All right, but there's a ton of other immune genes here, IL-6, Fc gamma receptors, GBP5, and IL-2 receptor alpha. Many genes here, even EOMES or TBET, and TBET and EOMES are both here, I believe, OASL. So one of the things that we've described along, in collaboration with Phil Scott is that this profile in the skin of these patients is really one characterized by a robust inflammatory response, and that many of those genes that show up in this list as being associated or induced in patients with disease, if you block those genes, you can actually also block the development of the skin disease, and that's work that Phil Scott's lab has done in mice. So really useful way to kind of move through your data and interpret it here directly in RStudio. Okay, so now that we've done that, we would like to actually pull out these genes, right? We'd like to pull out the genes that meet some cutoff criteria. And this is really important to understand, is that all differential gene expression really comes down to, at some point, drawing a line. And where you draw that line is really an arbitrary decision. There are certainly sort of common cutoffs like 0.05, 0.01 for adjusted p-values, log fold change of 1, which is a fold change of 2, or higher, right? Log fold change of 2, which is a fold change of 4. Ultimately, where you set your cutoff lines will depend oftentimes on your data. And no matter where you draw that line, you always run the risk, and in fact, you can be assured of the fact that there will be genes that are of interest and are biologically relevant that fall just below that cutoff line. And so that's a topic we'll deal with in the functional enrichment analysis when we will carry out gene set enrichment analysis, which operates on your data without any cutoff. So it'll look for pattern signatures, pathways in your data without you having to set a threshold for differential gene expression. Okay, so we're going to use a second function now. After following up on this top table that we did with Lima, another really useful function is the decide tests function. And what decide tests will do is it'll look at the Bayesian stats you extracted from that linear model fit, and it'll do a multiple testing correction using Benjamini-Hochberg, and you can set the adjusted p-value that it will apply and a log fold change. So these are your particular cutoffs. Here I've set some really stringent ones. A log fold change of 2 is a fold change of 4, and an adjusted p-value or FDR of 0.01, so 1%. Regardless of what you set here, what decide tests will do is it will then look at the stats from your data, and it'll go row by row through your genes or transcripts, and it will ask whether that gene or transcript in each row meets these cutoffs under the condition you've asked, in this case disease versus healthy, and it'll give a 1-0 yes/no answer. All right, so let's run this line of code and take a look at what we get out. All right, so it is a simple result here. It's a formal class test results, but the structure of it is really straightforward. Every row is your gene. You have a single contrast. That was called infection. And now I have a simple encoding of whether this gene met these cutoff criteria. 0 means it did not. Either it didn't have this log fold change, or it didn't have this p-value, or both. So it's 0. It did not pass my test. I see here this A2ML1 gene did not have a 0, it had a -1. And so that's the next part of this, is that any gene that does meet these criteria will get scored as a 1 in the result table here. And the sign in front of that 1 will indicate its direction of expression. So if it's a -1, it was downregulated it was higher in healthy compared to disease. And if it's a +1, it was up. Okay, so one thing I hope you understand is once you have this test result, it's super easy to parse. It is 0s and 1s, and the sign on the 1s tells you directionality. And so this is actually the structure you could use to make a Venn diagram. Now, I only have one condition, infection. So my Venn diagram is a single circle. But if you had infection and some other, if you had wild type versus knockout one and wild type versus another kind of knockout, you could have two Venns. The zeros, if you had a gene that was 0 in both columns of your contrast matrix, that would be a gene that's not differentially expressed under either condition. If you had a gene that was a 1 under one condition and a 0 under the other, that would be in one part of the Venn that's not intersecting. If you had a gene that was 1 in both conditions or both contrasts in your contrast matrix, then that would be a gene that was positioned at the intersection in your Venn diagram. And so these kinds of result tables are really easy to parse to produce summaries, to produce Venn diagrams and other kinds of graphics. So I can take this results and I can pass it to the function head, summary, or Venn diagram even, which is from the Lima package. And when I do that, it kind of summarizes this and gives me an idea. Okay, there were 10,056 ones and 1,258 ones and 1,258 ones and 1,056 negative ones. And there were 13,630 rows, genes, that were zeros. That then creates a Venn where that Venn will be a single circle with these two numbers summed together and in the middle. So that should be 2,300 and what, 16, something like that. Let's see here. Venn diagram. 2,314, okay? If I wanted not both ups and downs in that Venn, but just ups, I could change that. And now it's going to ignore all the negative ones, and it's just going to plot these 1,258 positive ones in the middle. So to create obviously a more interesting Venn diagram, you would need another contrast in your contrast matrix, another pairwise comparison, and it would plot that. Now, I wanted just a word of caution about Venn diagrams in general. They're useful sometimes, depending on what it is you're trying to say, but they can also be really misleading. The one way they can be misleading is that you use too many Venn diagrams, right? Too many circles here intersecting becomes really hard to appreciate the details. The other, I think, more troubling issue, for me at least, with Venn diagrams is when you show someone a Venn diagram, they immediately think in black and white terms, right? They think in ones and zeros and negative ones, even if they don't realize they're doing that. And so if you show a Venn diagram that has an intersection between two circles that might have 10 genes in it, and a set of genes that are not shared between your two conditions, let's say that's 20 genes over here, people think those 20 genes are really, really distinct from your other condition. And the reality is they may have just missed your cutoff, right? They may have just, not made log-fold change of 2 in both of your conditions, but they only did in one condition, so they end up over here. And the point is, some people can see a Venn diagram and then go and look at a heat map made from those genes and really wonder where the heck all their genes went that looked so different. And the reality is they may be actually very close to this cutoff and just missed it with one condition. So if you're having trouble visualizing that, I'm sorry, but just trust me that these Venn diagrams can be a bit misleading sometimes. All right, now what we want to do is we want to retrieve the expression data. Right? We haven't actually pulled these out yet, the genes with their expression data. And we're going to need those for clustering and other heat map stuff that we'll do in the next lecture. So what I'm going to do now is I'm going to take this variance stabilized DGE list filtered norm, and I'm going to capture the $E element. That's where the expression data resides. And if I want to take a look at that, right, we know that $E, let me go up, let me actually just highlight the DGE list itself. That $E is this, right? It's the data that we have here, log2 counts, okay? We're going to extract that, and to do that, we're going to use a simple subsetting operation, which is to say we're going to take the expression data from that DGE list, but we only want the rows. So I have an expression here on the left side of this comma, We only want the rows where the results in the first column, remember the results is my decide test results. There's only one column, but I have to indicate that column. If I had multiple contrasts here, I want to articulate which column I'm talking about. The pairwise comparison I'm interested in, infection, the result is not equal to 0, does not equal 0, right? So this is a Boolean expression here that we can use anytime. So does not equal 0. What I'm saying here is I want any row that was differentially expressed, that was a 1 or a negative 1. Right? And I want to use that expression to pull out the data for my differentially expressed genes. So just evaluating this part of the expression, I can see gives me a true false for each row in my data. And now any logical vector like this can be used to subset anything. So I can run this entire line, and now I have an object I call diff genes, which is just those rows of differentially expressed genes and their data. I can look at the top of that with head. I can look at the dimensions of that, and it's consistent with my very boring Venn diagram here. It's 2003-14, 2003-14. All right. So I pulled out all the things in my Venn. If you had a more complicated Venn with multiple circles, obviously, you can extend this by saying or, and for the or we use the vertical slash, or the results in column 2, like my other pairwise comparison, do not equal 0. Right? So that would say, you know what? You need to be a 1 in either this column, or you need to be a 1 in this column. If you're a 0 in this and this, I don't want you pulled out of this data. And so you could go on and on with these expressions, pulling out or setting criteria to pull out any slice of your Venn diagram. You could say, I want you to not be a 0 here, but be a 0 in this other one, or any sort of combination of Boolean operators here. So that'll let you pull out any chunk of differentially expressed genes that you want. Once you have these differentially expressed genes, right, we often convert things to a tibble so that they play nice with the tidyverse. So we can go ahead and do that. And then now that it's a tibble, we can make an interactive table if we'd like, using that DT package that makes interactive data tables. And we used this already once before, so I'm just going to run this line of code, and we will get now these 2,314 genes will be displayed as in the viewer tab as an interactive table that I can search. And so that MMP1, very well better be here, and there it is, right? With this, huge fold change between my second 5 samples and my first 5 samples. Okay? So that at this point, you know how to make a volcano plot, you know how to make a table of your differentially expressed genes, and you understand this process of setting up a linear model, extracting the linear model fit using your contrast matrix, putting together or pulling out Bayesian stats for that linear model fit, and then running top table and decide tests to actually then extract and get the genes that you want from your statistical tests. We'll pick up with this last part in the next video.